Last time we started to calculate the first loop correction to 2-point function in a scalar field theory. Okay? So this is from the previous lecture. The model that we were considering was a scalar quantum field theory with interaction Lagrangian, which has only a cubic term. The bilinear part is universal for all scalar field theories, therefore I will not write it. The important thing to calculate the loops is just the interaction part. And we start calculating the 2-point function of the Heisenberg field operators and showed that if you expand this in power series of this lambda 0, there will be, of course, the 3-level part, which is the Feynman propagator, plus a one-loop correction to it. And in the momentum space, in Fourier space, this becomes I divided by p squared minus m0 squared plus I epsilon plus I divided by p squared minus m0 squared plus I epsilon. This piece we called I of pi, I times pi of p, and our main business was to calculate that part. So this is p, p, p. So this was the real problem, was to calculate this blob here. Okay? That's the loop part. The rest is just factors which multiply that in the one loop correction. And we showed that that integral, we showed that minus I after the weak rotation, etc., it reduces to lambda 0 to power 2 times I. Then there was a Feynman parameterization of the propagator, and the rest was an n-dimensional Euclidean integral, or integral n-dimensional integral in the Euclidean space of we call this object here minus a squared or plus a squared, and called the whole integral in, including the factor of lambda 0 over 2. No, excluding that factor. So, and the whole thing therefore reduced to in of p, which was dnk over 2 pi to the n 1 over k squared plus a squared to the power 2. And the trick was to rewrite this denominator as an integral over a parameter s, and then perform the Gaussian integrals. The rest is just Gaussian integrals. And we did that. The result was expressed in terms of gamma functions. So let me write one more step and yeah, let me write one more step and then write the result. Next step was integral from so we calculated this, expressed the result as in terms of a common function. This is the result of integration over basically over everything. Okay, this is where we arrived. Now, the important thing is that the gamma function has simple poles at when its argument is 0, -1, -2, -3. And you see that if n is anything, if n is 4 or bigger than 4, if it is 4, this is 0. If it is 6, that's the case that we are examining, then this will become of -1, which will have a simple pole. Okay? And the idea is to separate the pole part plus the rest. The rest will have, so since we are interested in this particular case for n equals to 6, we introduce a parameter eta, which is defined to be 6 minus n, and then write everything instead of n, write everything in terms of eta. So in particular, this object here becomes eta over 2 minus 1, the argument of common function. This one becomes a squared times a to the power eta, for example. So therefore, one more line. This factor, we can write this 4 minus n from here. You see that should I go through all these steps? I think I did this last time, no? Did I do that? Maybe then I should go to, I don't remember where we exactly arrived. Did we expand the gamma in powers of e? Sorry. Okay, then let me jump into the final point. One other point that I want to remind you, this should go, of course, here, okay, to construct pi. And this is pi of p, not p, to construct pi. And another important point here, not so important for what we are doing, but it will be important later on, was to argue that this coupling constant here has dimension. When we go to arbitrary dimensions, its dimension, mass dimension, becomes independent. Okay? So we introduce an arbitrary mass parameter and wrote lambda 0 as some mass parameter mu to the power which absorbs the mass dimension of lambda 0, essentially. And then times a dimensionless parameter lambda. So we will write everything in terms of that lambda and mu. And so I'm not going to write SI anymore. I will write the result for minus pi. The I from here cancels the I from there, therefore you simply get minus pi. There is a lambda 0 square. You have to take the second power of this. I think I'll do it the same. notes, there must be a sign error. That should be plus, yes, sorry. You should correct it also in the notes. I think it's a typo. So this is mu to the power eta. Lambda 0 squared gives you mu to the power eta. Not lambda 0, but lambda 0 squared gives you lambda to the power 2, mu to the power eta. Because when you take what you need here is the square of lambda 0. The square will give you mu to the power 6 minus n. And 6 minus n is eta. There's a factor of 1/2 in the original expression. Then even the 4 pi to the power n over 2 can be written in terms of eta. And it becomes, so you have to substitute for n over 2 here, and it becomes 3 minus eta over 2. Then we expanded the gamma. Here we have gamma of eta over 2 minus 1. We gave a formula. That formula for our case starts with a minus sign. Therefore, there's a minus 1. Then there is a singular term, which is 2 over eta. There is a constant called Euler constant, plus 1. These all come from the expansion of gamma. And then there is the integral over the Feynman parameter x, lower rank. So this whole thing will multiply an integral over the Feynman parameter x. And in the result, you see that you have a to the power 4 minus n. You can write this as a squared times a to the power minus 6. Sorry. Anyway, substitute. I'm trying to be too detailed on the blackboard and making a mess. So, if you substitute for eta from there, you should get that power. If I haven't made a mistake with the signs. This is the
minus 1 plus eta.
Sorry? Oh, I seem to have made. Oh, this is n minus 4, not 4 minus 4. N minus 4. Yeah, it's n minus 4, not 4 minus n. Sorry. And there's another T point. No, in the notes it's okay. Okay? Are you okay? Now, first of all, you see that this term can be combined with this term. This mu to the eta. In fact, also the eta dependent part from here. So mu to the eta divided by 4 pi to the power of minus eta divided by 2 times a to the minus eta. These are the only places where eta comes in these terms. The other place is the singular piece here. Okay, there is no other place where. Of course, here there were terms which are positive powers of eta, but they will not contribute when eta goes to 0. So you can put all of them together. You can write this mu divided by a and 4 pi, square root of 4 pi, and the whole thing to the power eta. This 1/2 gives you the square root of 4 pi. There is minus eta here where it goes to the numerator. You can write in numerator with positive power and you get that. So this whole thing becomes this. Okay? The idea is to write this as exponential of eta times logarithm of the rest. And then now you can expand in powers of eta. This is an exponential. It gives you 1 plus a term which has the first power of eta. plus a term which has second powers of eta, etc. And this is going to go into this place. Okay? So, let's make that substitution. I am doing this probably in more detail than what's necessary, but we will not repeat this detail in other similar calculations. I would like you to see what we are after. So this minus sign from here cancels that minus sign from there. So we obtain a formula for pi of p squared. Then there is the coupling constant in front that we should write with its factor of 1/2. The power of 4 pi was 4 pi to the power 3 minus eta over 2. We only wrote this part. So there's a 4 pi in the denominator. There is a 1 over 4 pi to the power 3. This minus we already took care of, cancelling against that minus sign. And therefore, there is the only thing which is left from there is that 2 over eta minus gamma plus 1. That's the singular piece. And then times that integral. So that will multiply 0 to 1 dx a to the power 2 as 1 plus eta times the rest. That's the result of our calculation. You have to remember that this a is a function of p squared. A is defined here, and you see that it's a function of p squared. Okay? Now this gamma itself also can be written as exponential of logarithm of gamma, etc., can be absorbed in here. So I'm going to drop that constant and put the gamma here, exponential of minus gamma. Its sign was minus, so it becomes exponential of minus gamma. So the role of this square root of 4 pi exponential of minus gamma, these are just numbers, is that to replace this mu by another mass parameter. Just it's equal to this number, to whatever this mu is, an arbitrary mass parameter anyway. It's this times this constant. You will call it mu tilde in order not to write this chunk too many times. Okay? You will just call it mu tilde. Later on we will discuss the role of these constants a little bit. But for what we want to discuss now, they have no importance whatsoever. Now multiply, identify the singular piece and the finite piece which is independent of eta. So when we multiply, there is this 2 over eta times this one will give you a singular piece. And so let me explain and then write the final result. There's no point in going through all the steps. So you see that this term times this times 1 will have a 1 over eta in it. Okay? And it will diverge when eta goes to 0. But then in a squared you can do the integration over x, because the dependence of a squared on x is something very simple. It's x times 1 minus x. So in the singular terms, let me do that integration here. In the coefficient of 1 over eta, we will have dx from here times a squared, which is dx times minus b squared x times 1 minus x plus m0 squared. Okay? And this integration goes from 0 to 1. Obviously, the integral of dx times m0 squared gives you only m0 squared, and this is a simple function of x. You can easily integrate, and the result of this will give you m0 squared minus 1/6 times p squared. So I'm going to write that object here. There is a 2 here and there is a 2 there. Therefore, in the singular terms, we will get lambda to the power 2 divided by 4 pi cubed times 1 over eta times m0 squared minus 1/6 of p squared. Then there is this 1 times the rest. So that 1 times a squared terms will give you a p squared dependent term, which is independent of eta. There also you can use that formula for the integration. Therefore, that term will give you lambda squared over 2. Here, the factor of 1/2 will not cancel. Then the rest is identical. This is independent of eta. Therefore, when eta goes to 0, this term will survive. This will diverge. That will survive. What other terms are independent of eta? Clearly, if you multiply this term with this term, the 1 over eta from there will cancel the eta from here, and you will get an eta independent term. The 2 from there will cancel the 2 from there. Therefore, we will get lambda squared divided by 4 pi to the power 3. The etas will disappear, and we will get 0 to 1 x a squared log of mu tilde divided by a. That's it. Then the rest, all the positive powers of eta that we had here, eta squared, eta cube, etc., multiplying the singular term, they will give you terms of order eta or higher. They will disappear when eta goes to 0. Right? And likewise, 1 from here times anything which has positive power of eta will go away. So this is what we get after all this analysis. Okay? Any questions? Good. This is more or less the general feature that you get in any one-loop calculation. So any one-loop calculation will involve integrals like this. I mean, not any, but okay, the generic structure will not be like this. For example, if in the same model you are calculating a 3-point function, then there will be 1, 2, 3 propagators. So there will be the product of 3 propagators in the denominator. There is a more general Feynman trick, which you can put the 3 propagators in a single denominator and write power 3. Then the rest will go through. However, you have to introduce 2 Feynman parameters here, and that by itself makes the calculation more complex. These little integrations from 0 to 1 over x, you have to introduce. As the number of propagators in the denominator increase, you have to introduce more of those integrations. And they are not trivial when the number of propagators become large. Okay? So we will not do a calculation like this, but after you have done it, then you can use dimension regularization, apply similar tricks, etc., and one loop results always will end up with the sort of operations that you are doing after you have done the weak rotation, Feynman trick, and then you will end up with similar things. Okay? What will change is that when you are writing the denominator as an exponential, then the factor of s that we put in the integrand, that power can change. If this power 2 2 is different. Things like this, the little details will change, but the general features will remain the same. That's the reason I went through maybe too much of detail on this calculation. If you learn this, essentially you have learned the rest. This is what I meant. The rest as far as the one loop graphs are concerned. When you go to higher than one loop, then there are other features that we have to learn. Okay? Now that we have obtained pi of p squared, the question is what to do with this. There is a piece which obviously diverges. And then there are pieces which are convergent, very well-defined expressions. There should be a physical principle to guide us how we should handle this divergent piece from here. At the end of the day, we will learn that just throw it away. But that throwing away should be done careful steps, and after we have learned a few other things. Okay? And there is more than one way of throwing it away, because this is an infinite quantity when eta goes to 0. You can throw the whole thing away, or you can write this infinite quantity, you can take some part, finite parts from it, and go put it there, and then throw the rest of it. Therefore, we have to know how we are going. The infinity plus some finite quantity is again infinity. Okay? So, for example, I separated the 1 from here and wrote it as a separate term. But if the throwing away is the rule, I could have thrown away this whole thing. Therefore, there should be some other things, a little bit of discussion before we throw away the divergent piece. So we want to do that the rest of the discussion, to see what's going to guide us. And for that, I'm going to write down the exact propagator, not one loop approximation, but the exact propagator in two different ways. The first way will be dictated by the graphical expansion. And the second way will not be dictated by graphical expansion. In fact, it will not be dictated practically by nothing apart from relativistic invariance of the field theory that we are discussing. Okay? We will not use any dynamics, any field equations. We will just use the relativistic invariance, relativistic symmetry of the field theory, and some assumption about the physics of the problem, not the calculations. So first, the graphical one. What we want to do is to discuss the exact propagator. That means exact 2-point functions. So the first way is the graphical. To discuss this, I have to introduce some notions of the Feynman graphs, some definitions essentially. Recall that what we are calculating essentially is the generating function of z of j. We are calculating the derivatives of this function with respect to j. Or if you expand this in powers of j, we are calculating the coefficients of those expansions in powers of j. J to the n gives you the n-point function, essentially. No? That's what we are calculating. Now, when you expand this, you get all possible graphs, connected and disconnected, first of all. For example, just to give you an idea, let's consider the 0j. We calculate this explicitly, and it was that function. That was our calculation. That's an explicit expression in terms of j. It's Gaussian. If you expand this, the first term will be 1. The second term will be 1 power of this. It has 2j and 1 delta. So we will represent it like this. These are the j's. That's delta. The second term will be the second power of that, times factors of 1 over 2 factorial, etc. And that will be 2 copies of this. Disconnected 2-point function. Disconnected 4-point function, which is obtained from the product of 2. And then the third power will give you a 6-point function, but disconnected. So in this model, if this was your theory, you will only get the disconnected graph. There will be, apart from the first one, the rest will be just the product of the final propagator. Okay? When you go to interacting theory, the one that we are considering, we saw that for the 2-point function, of course you get this one, plus for 2-point function, you get this, and then you get plenty of other things. The one that we are calculating is this. We have dropped these j's at the end, but that doesn't affect this discussion. Huh? If you're expanding z, that's what you get. You'll get other functions, for example, this in this model. When you go to 4-point functions, you can get this disconnected piece. But you can also get a connected piece like this, etc., etc. So you get all sorts of graphs. The only ones that I am not writing are the ones which have disconnected vacuum bubbles. We saw that they disappear. Okay? There is enormous amount of redundancy here. So if we want to evaluate, if we want to analyze this problem, we have to reduce it to the basic irreducible parts. Otherwise, we will be repeating the same thing infinite number of times because there is plenty of redundancy. If we come to this example, you see that the only non-trivial information here is contained here. If you know what this is, the rest are all the products of the same thing. Okay? So we don't need to consider all this. It's sufficient to consider this. If you come here, you see that this is a sort of irreducible piece. You have to take that into account. This one is also an irreducible piece. You have to take that into account. But this one is just a product of two of them. So if you know what this is, just multiply them and you'll get this other 4-point function. On the other hand, this one has an information that you cannot obtain from here and there, from the previous terms. You have to actually calculate this. Okay? That the information contained in it cannot be obtained from the previous ones simply by multiplying graphs of lower order. So this remains. Therefore, the set is decomposed into connected and disconnected graphs. The disconnected graphs do not have any genuinely new information. If you know how to handle the connected graphs, you also know how to handle the disconnected graphs because they are just products of the connected graphs. It will be much nicer if we had a generator functional which generated only the connected graphs. Then you wouldn't be dealing with a lot of redundancy. Surprisingly, this generating functional is very simply connected, simply related to this one. The relation is that if you write this as I times some other functional of j, that means if you take the logarithm of z and divide by I, then derivatives of this functional will produce only the connected graphs. That means you will not, if you expand this functional in powers of j, you will not see these ones, you will not see these ones, and other disconnected graphs. In the case of this one, it's simple to see. Because if you write this as exponential of I times j, then you see that W of j is simply I divided by 2, j delta j. So only the second derivative of that with respect to j at j equal to 0 is non-zero, and that gives you the final propagator. So it gives you only one part, and that's connected. Here, it's not so obvious that in the interacting theory, if you define this W simply by taking the logarithm of z, or writing z equals to exponential of iw, then the expansion of W will produce only the connected graphs. Okay? However, it's not hard to see. Maybe in one of the future lectures, if you don't do it in tutorials, probably in one of the future lectures we will see it. For the time being, in order to convince yourself You can take the derivative of this and calculate the endpoint functions coming from here. You will see that the disconnected pieces appear. It's some low order so that you can handle the evaluation of the derivative doesn't become too complicated if you haven't seen this before. But you can give a full proof that, I mean, it's not hard, but I don't want to digress now to discuss that. Okay? That we will do later. For the time being, I want to just tell you that there is a way to write the whole thing in such a way that when you expand W, then W will give you, the one will be, that's here. So the W will give you this, plus this connected piece will be there, this will be absent in W, that will be there, etc. Only the connected pieces will be there. Are we clear? Now, this is one way of reducing the number of things that we want to examine, just eliminating all the disconnected graphs. But then there is another step. For example, there is a contribution to the two-point function, which is like this. That's a higher order correction of this graph. Okay? We see that there is also redundancy here. Why? This is just finely unpropagated, that's finely unpropagated, that's finely unpropagated. If you cut this from here, essentially each piece will be a copy of that. So this really doesn't carry any new information. You can just take this away, this line, cut this line, and then, or if you know this, you can construct the expression for this one, the algebraic expression for this one. Right? So the graphs that you can cut into two disconnected pieces by cutting an internal line, this is an internal line, we are not cutting here or here. We are cutting an internal line. Such graphs are called one particle irreducible. One particle means that you are cutting one internal line. If you cut more than one internal line and separate them into pieces, then it will be called not one particle, but two particles irreducible, three particles irreducible. These things have been introduced and studied. But we don't want to do this. So we will stick only to one particle irreducible graphs. The graphs that you cannot cut into two different connected pieces by cutting a single internal line. Okay? So this is the further simplification of our task. So let me just summarize what we are doing here in order not to forget. So Z generates all the graphs. By all, I mean all the graphs without the vacuum, disconnected vacuum bubbles in it. W, which is 1 over I times logarithm of Z, generates all the connected graphs. And then in the set of the connected graphs, we have reducible, one particle reducible and one particle irreducible graphs. So the connected graph can be one particle irreducible or one particle reducible. We would like to stick with these ones, one particle irreducible graphs. But that's not it. We can simplify them further. So let's go to the graph which we are examining. One particle, this is a one particle irreducible graph. Where is the new information in this graph? New meaning new beyond the tree level. graph that we know what it is. The 3 level, this is a correction to the Feynman propagator. So at the 3 level, it's just Feynman propagator. There's a Feynman propagator here, there's a Feynman propagator here, but there is some other object here which is more complicated. Obviously, there's no new information in these legs that we have attached to it. But the new information is actually connected in this part from which we have removed the legs, external legs. If you go to higher pieces, for example, if you go to a higher correction to the same object, there will be a graph like that. This is one particle irreducible, it's connected with one particle irreducible, but again, the information is contained in this piece. Okay? So take any graph, remove any one particle irreducible graph, remove all the external legs, what is left is really the object which carries the information that you need. Okay? That piece is called irreducible vertex. One particle irreducible vertex. So here, this is a 2-point irreducible vertex here. This is a 2-point irreducible vertex. Okay? If you go to more complicated corrections, we will make this graph more complicated. I don't know, you can put like this. This means that the lines do not intersect each other. You can make it as complicated as you like. This piece is called irreducible vertex, 2-point irreducible, because it has 2 free ends to which you can attach. So, these are the objects which carry actually all the useful information. If I know this one, this one, this one for any complicated 2-point irreducible graph, I know everything about the 2-point function. So what we want to do now is to introduce a notation. The notation is as follows. So we are going to call with the same notation pi. Let me first give the graphical presentation of what I want to explain to you. So let's call this minus I pi p, and let's assume that it denotes the sum of all irreducible 2-point vertex. That means it's the sum of all of these vertices. There are infinite number of them. Okay? So in the one loop approximation, that thing will be just that. If you go to more than one loop, it will be the sum of graphs like this, etc. If we know this, then we can just glue them together and construct the 2-point function. So the exact 2-point function, E2 of P will be delta, will be the tree graph plus 1 of this, plus you can glue them together, 2 of them, plus you can glue them arbitrary number of them. So this sum will include all the connected one particle irreducible, all the connected graphs, not one particle irreducible. These are one particle irreducible because you can cut from here and reduce it to 2 pieces. Okay? But eventually it includes everything. all the connected pairs. It doesn't include the disconnected pair, because you can put, if you want to count, in the case of 2-point function, that's not, well, I think these are all connected. But if you go to 4-point function, you can put 2 of them together, or you can put one of this and one of that together, and that will be a disconnected contribution to a 2-point function. The connected contributions are all constructed in this way. Am I clear? Any questions? Okay. Graphically, you see that this infinite sum actually can be written in a compact form, okay, as a single expression. And in order to see that, let's put the values of the Feynman propagator in various places. Let's introduce symbols, in other words. So what we are saying is that G2P equals to delta F plus delta F times minus I pi times delta F. The next term is just the square of this. No. Minus I pi delta F plus dot 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 dot. It just continues like that. So this term is that, the next term is this, the term after that is this, and you can write a string of them. Okay? Well, we can write this as delta F. If you put this as a common factor, then inside the bracket you generate again the same object. And this is again our G2. So if you take the G2s to the same side, you have G2P, there is 1 from here, there is minus delta F minus I pi equals to delta F. Well, this is this times G2, I took to the other side and factored the common G2. Therefore, G2 of P equals to this delta F divided by 1, the minus, that minus becomes plus, I times delta F. Delta F times pi. Okay? If you put the value of delta F in this expression, we know what delta F is. It is I divided by P squared minus M squared, epsilon, etc. So it becomes I divided by P squared. I'm going to put this value and multiply the denominator. Multiplying the denominator gives me P squared minus M0 squared plus I epsilon. And then this expression times that gives me an I. That I times this gives me minus I of P. Okay? I multiplied basically the numerator and denominator by delta F to the power minus 1. Or some I times that. So that's the expression for the exact 2-point function. This is one expression which I told you we will obtain using graphical methods. And this method that we are doing is not specific to the model that we are examining here. It is completely general, and plays an important role in renormalization theory, in QED, in every field theory that you want to study. We are deriving in the context of a very simple toy model, but the expression is general. General in the sense that when you go to higher spin fields, the only thing, or one of the things which happens, is that the fields carry spin. This means that objects carry indices. Everything becomes matrices. For example, for fermion propagator, you have a matrix here. In 4 dimensions, a 4x4 matrix. Everything becomes matrix, and you have to keep the track of those matrix indices, but the general expression will be of this form. There will be a free propagator here plus this piece, which is called vacuum polarization piece, or mass operator sometimes it's called. Okay? The general structure will be of this type, interpreted properly as matrices. You will see that in QED, for example. Any questions? Okay, this is the end of my discussion of the graphical way of obtaining exact two-point function. In the rest of the time, I'll try to obtain the second way of doing it, which is not graphical and will not use any specific feature of the Lagrangian that we are even examining, but the general relativistic invariance of the problem. So the second way is what's called spectral representation. So recall that we are examining two-point function, and which is the time-ordered product of. So we are examining G2, x1 minus x2, which is there will be no perturbation theory in what we want to discuss now, and no graphs. Now, this object is the sum of two terms. One is the product of these operators, this coming first, that coming next, times theta of x01 minus x02, plus in the opposite order. The same thing in the opposite order. Right? So let's consider for timing, I will drop these subscripts because we are dealing only with Heisenberg fields. So it's understood that that is what we want to do. The Heisenberg fields, everything carries a subscript H, if you like. There is no free fields in this discussion. So, I mean, they will come, but later. Okay? So this is the same expression without a time ordering. If I know this, then I can multiply this by theta, and then I can interchange x1 and x2 and multiply with appropriate theta, add them up, and then I can obtain this. So therefore, this is the object that you should study. And to study that, the trick is to insert a complete set of states here between the two operators. We can obtain the result that I am telling you can be obtained in other ways, which is generalizable to the product of more than two fields. But in this particular case, it's easier to do it the way that I'm doing it. Not easier, but it's customary, if you like. However, we could do it also in a way that if you had more than two fields, then you will discover what the answer is. The answer that we are going to obtain will be generalizable to other cases. And I'll make a comment about that later. So what we want to do is to insert a complete set of physical states here. And the emphasis is physical. Complete set of physical states.
How is a physical state defined here?
Good. So that's where we are going to use the relativistic invariance. So the relativistic invariance means that there is a bunch of operators In 4 dimensions, there are 10 operators, which we discussed in September, if you like. 6 of them are the generators of the Lorentz transformations, and 4 of them are the generators of the translations. These generators generate the Poincare algebra in 4 dimensions. If you go to higher dimensions, n dimensions, the number changes. Instead of 6, you will have how many generated Lorentz generators in n dimensions?
What's the question?
The question is that if you go to n-dimensional Minkowski space, how many generators does the Lorentz group have?
N square minus
Oh,
n
sorry.
over 2.
N over 2 times n minus 1. It's like orthogonal group in n dimensions, and these are the antisymmetric matrices for the orthogonal group. So n over 2 times n minus 1, which is 4 dimensions, it becomes 6. The number of generators is always the same as the number of the dimensional space time. Okay? For the relativistic quantum theory, the object that we need is the unitary irreducible representations of this group. This is a non-compact group. Its unitary irreducible representations are all infinite dimensional. Unlike SU2, which is compact, and its unitary irreducible representations are characterized by a discrete variable, which is called the angular momentum over spin. J equal to 0, 1/2, 1, 3/2, 2, etc., etc. Here, you have infinite dimension representations. The unitary representations are because of the topological property of the group, which is non-compactness, they are infinite dimensional. Now, one way of defining a particle is a unitary irreducible representation of the Poincare. That means with every particle, you attach a set of quantum numbers. These quantum numbers are eigenvalues of the Casimir operators of this algebra. Casimir operators are the operators, how are they defined?
With all the generators.
Which commute with all the generators. They are multiple in every irreducible representation. By Schur's lemma, they should be proportional to the identity operator.
Yeah.
The coefficient of proportionality is what defines for you the physical quantities. For example, so now let me write in terms of equations instead of in terms of words. Poincare algebra. We have P mu, momentum operator, and M mu mu, the Lorentz generators. Okay? So one of the Casimirs is P squared, which is P mu, P mu. The other Casimirs are constructed from the product of this with that. I mean, there's in 4 dimensions the famous Pauli-Levinsky vector you probably have seen, but we are not going to use them because we are going to apply the whole system to the scalar field theory, and there's no spin or other quantum numbers. So we will stick with this one. But there are more Casimirs depending on the number of dimensions. Okay? The other ones are relevant if you are dealing with spinors, for example. Okay, so let's take, to apply to our problem, the only relevant operator is this, which is called the momentum operator. So P mu's are momentum operators. And they're Hermitian. And they all commute with each other. Therefore, you can diagonalize all of them simultaneously, all of the p's. So we will denote its eigenvalues and eigenvectors. We will denote eigenvectors, so eigenvectors of P mu, we are going to denote them by n. And P mu acting on it it will give you an eigenvalue p mu n. This n refers to the state times n. This is symbolic way of writing. You know that the eigenvectors of the momentum operator usually for a single particle you denote by vector k or p or something. But I do not want to prejudge the notation. I'm writing it as n because we are not going to deal only with the single particle states. And since p squared is proportional to the identity operator, let me call it m squared times, no, how should I write it? Right, this is Casimir. I will very quickly run out of symbols if I use m, and I use m for everything practically. So this means that the eigenvalues, when I put this square, this means, let me write this explicitly. This is mn squared. In every representation, it's proportional to the unit operator, and the unit, the coefficient of proportionality, we call mn squared. When n changes, we go from one eigenvector to another. Okay? And correspondingly, the eigenvalue changes. Now, here are another way of saying what the physical states are, or some statements about the spectrum of eigenvectors and eigenvalues of this operator. So the first assumption is that there is a lowest eigenvector, which we denote by vacuum, on which all these operators act and leave zero. And then there is one particle state on which p squared acts and gives m squared times that one particle state. What's m squared? M squared is the lowest eigenvalue above zero. It could be zero itself in the case of massless particles. But for the massive particles, it is the lowest eigenvalue above zero. Okay? And then, of course, there are plenty of eigenvalues. For example, if there is a bound state in the spectrum of this problem, there is an eigenvalue which is just about m squared, above m squared, but below for m squared. Because if this is the mass of a single particle, then if you have two of these particles free, their mass will be 4m squared. However, if they form a bound state, their mass will be smaller than that. Therefore, if there is bound state in the spectrum, there will be something above this and below 4m squared. Above 4m squared, there will be a continuum, and we will come to this continuum in a minute. Okay? However, the assumption is that such states do exist for a massive particle. If you want to use this field theory for a massive particle, the momentum eigenvalues should square to give the mass of that particle. And this is the physical mass we are talking about. So m squared is physical mass squared of a single particle state. Here there is no Lagrangian, no perturbation theory, nothing. So to start with, there is no relationship between this and what we call m0 squared. These are two different things. Okay? This object was introduced when you introduce an action, Lagrangian, etc. Here there is no action, no Lagrangian. We are just talking about the eigenvalues of a Hermitian operator. So we should not confuse the two things. We will see how they are related to each other, but not at this stage. And then there's another assumption. In order for these eigenvectors to be physical, we assume that the time component of these vectors to be positive. So the time component, because of this, is related to the space component plus n squared. So if you take the square roots, there will be two roots, one with positive sign, the other one with negative sign. The eigenvalue of p, the eigenvalue of p0n for the physical state should be positive. Physical particle should have positive energy. So these are basically the assumptions. The other thing is the group theory. The group theory means what's the role of the operator p hat? What does it do when it acts on a field? What does it do? It translates the space-time points as the generators of translation. So here comes the group theory property. P hat is the generator of translations of space-time point. That means it represents the operation of translation of space-time points in the Hilbert space of quantum states. Written in terms of operators, this means that exponential of I, a translation of by a mu of the space-time point phi hat x, exponential of minus I, a mu, p mu. This takes you from point x to point x plus a. That's the meaning of that. In particular, you see that from here you see that exponential of I, x mu, p mu, phi hat 0, exponential of minus x mu, p mu, takes you from the point 0 to the point x. Okay? That equation tells you this, that you can obtain the field at point x from starting from the origin and making a space-time translation. Now that we set up this background, we go back to our two-point function. Any questions? Okay, so probably you have seen this in Giovanni's course, right? You have seen that? Okay. You should have told me, or I should have asked you before, then we would have saved some time. So we were examining, have you seen also the spectral decomposition of the two-point function? Yeah.
The graphical we did. We did already the graphical in psychophysics.
Graphically, okay. So we said that we take this one and insert here a complete set of eigenstates. By complete, since they are complete, that will be 1. So that's where we want to insert it and use this formula to write phi x in terms of the momentum operator, use the fact that these are eigenstates of the momentum operator, and therefore rewrite the whole expression in some way. So this will give you ground state, it will give you a sum of ground state. Can I also at the same time substitute for that object from here? Maybe to save time, I x mu, p mu hat, that's x1, phi hat 0, exponential of minus I x1 mu y hat mu times n there is an n here, then exponential of I x2 mu of phi hat 0 exponential minus I x2 mu ground state.
Either
What?
B.
Exponential of the second part.
Oh, sorry. Thank you. We said that the ground state is killed by p hat. So this acting on this gives you, what does it give? It gives the ground state itself. It doesn't give 0. P hat kills it. Exponential of p hat doesn't kill it. It acts like unit operator. So this gives you 0 of phi hat 0. And this acting on that gives you the eigenvalue corresponding to state. So it's n. I am going to write the eigenvalues likewise here. It will give you the eigenvalue. Then there will be phi hat 0. This acting on that will give you 1 times exponential. One eigenvalue will come from here, one will come from here. So it will be minus I x1. The eigenvalue will be p. Let me put pn dot x1 minus x2. I suppress the indices mu. So this is pn mu x1 mu minus x2 mu. It's clear? So we sum over this infinite number of states. These objects here are constants. And they're complex conjugates of each other. So I can write the whole expression like exponential of minus I pn times x1 minus x2 times modulus square of n phi hat 0 0 n. The whole idea of the spectral representation is to write this whole expression and later on the 2-point function, which is the time order product, the same thing, as much similar to the free particle as possible. So we will see that in fact it will be just the sum of the free particle propagators, superposition of free particle propagators. This is the aim. That's where we want to arrive. Okay? We want to show that this thing, or the 2-point function, can be written as a sum or as a superposition of Feynman propagators for free particle states. This is the whole idea of the spectral representation. To do that, we have to do a few things. The first thing is that this sum goes over all the physical states. In particular, it goes over the ground state, single particle state, and the multi-particle states. We are going to separate the contribution of the single particle and one particle states, and then write the rest. So let's do this. So separate the ground state and the one particle states. The ground state, we said that has 0 momentum, so this will be just 1, and that will be the ground state. So that object is the ground state. Plus the one particle state. We know how we should write the completeness relation in the space of one particle states that we know from, this is the momentum eigenstates, and this is the way you normally write the contribution of the one particle states. I will make a comment about this omega squared in a minute. Exponential of minus I, oops, in the note, the K is missing from here. I change the notation from P to K for the single particle state. Let me first write this. So we are expanding the sum, the ground state, just the ground state I wrote here. The one particle state, the completeness relation is like this. Here, omega squared is the standard thing, except that the mass which enters is the physical mass. Okay? It's the physical mass enters into the definition of omega, because we are inserting physical states. And then the rest is standard. Plus, the sum of terms, which I will put a prime on the sum in order to indicate that we have separated the ground state and the one particle state, so they should not be included. They should not be included in the sum anymore, because we have already taken care of them. Okay? This is the result for that calculation. Now here comes the crucial point. The crucial point is that the first term, which is a constant, is either 0 or it is not 0. If it is not 0, I can simply redefine phi by subtracting this constant from it, and then redefine phi will have zero vacuum expectation value. Okay? So if it's different from 0, then the operator phi hat prime defined by, so let's call this C. Then this will have vanishing vacuum expectation value. And then I will use this operator to work everywhere, not that one. Okay? So we just drop this because we can make it vanish by simply shifting the operator phi. This has, of course, implications, because it means that if you start from your Lagrangian, now let's make a link to the Lagrangian, and there you have the fields phi, you have to make a shift like this, then that shift should be done in all the terms of the Lagrangian. And if you have phi cube term, for example, it will also shift the coefficient of phi square term. It will create a term proportional to phi. Okay, phi to power 3, if instead of phi you replace phi plus a constant to power 3 and expand it, you will get not only phi to power 3, you also get some constant times phi squared plus some constant times phi plus some constant cubed, the constant by which you are shifting. That's the expansion of phi cubed. Okay? So we have to remember that this shift will imply that the coefficients of the terms in the Lagrangian will change. The second term is this. The first part is standard, but here you have a thing which seems to depend on k. However, the whole thing, the whole formula seems Lorentz invariant. Its k dependence can only be true for dimensional k squared. So k phi hat 0 ground state can only depend on k squared by Lorentz invariance. However, the states are mass shell states, and k squared is just the mass of the particles squared. So that means that this is independent of k. It's just a constant. Okay? This constant normally is denoted by z to the power 1/2. So that the thing which goes here becomes z squared. Now, of course, you can redefine your phi by dividing it by this constant and obtain a phi for which that constant is simply 1. So I can define, if I find space on the blackboard, so redefine phi, the phi hat you start from, define a new phi, so introduce a new phi. I will attach a label R to it to distinguish it from the original one. In fact, the original one I will call bare, and this one I will call renormalized, because we are renormalizing this field operator. So this is field renormalization. Historically, it is called wave function renormalization, but there is no wave function. It's just a field operator renormalization. So we define this new phi, the new field operator, by simply saying that this equals to z to the power of 1/2 times phi renormalized phi. Now going back here, or going back to the reasoning that we made about the momentum eigenstates, this essentially means that the vacuum, the transition of the renormalized phi between a single particle state of momentum k and the ground state is I k dot x. If you go back into the way that we inserted the complete set of states, etc. here, that's what it implies. Whereas if you write in terms of the Bay field, it would be z to the power 1/2 times I k squared. So the renormalized field will have a dependence on x will sandwich between the single particle state and the ground state, which is precisely like the one of the free particle. Okay? This is a very important assumption. Again, if you go back to your Lagrangian, in the Lagrangian, of course, the field doesn't satisfy this property necessarily. But I can write the Lagrangian in terms of this field by introducing a constant z and expressing everything in terms of the renormalized field with the property that I expressed here. Okay, so we should remember the field will be shifted. It will change the coefficients of m squared, the constant part, and also phi cube term. Not phi cube term. The field will be renormalized by multiplying by z, and this renormalization will change the coefficient of every term in the Lagrangian, because every term has a phi in it, including the quadratic term. So the phi squared term, phi cube term, phi term, everything will have a z in it after we have made this rescaling. Okay? Oops. I'm already over time. Can we go another 5-6 minutes?
Okay.
If you are tired, we should stop.
We are tired.
You are tired? He is tired. Who else is tired?
How much is left? Otherwise, to finish the idea.
No, at least 7-8 minutes, not more than 10 minutes.
Okay.
No, we can stop. I mean, there's no compulsion to continue if you're tired. Is everybody tired? We will stop. If one person is tired, that's okay. Especially since he already knows everything.
Can you say that because when
First of all, let's decide, are you going to stop or continue? Who wants to stop? Please raise your hand. Who wants to continue? Please raise your hand. So everybody wants to continue. Let's continue, then we will discuss the question. Sorry, you want also to continue or you want to stop?
I raise my hand.
You raise your hand. I didn't see that. Okay, thank you. Okay, so let's continue and so that. Good.
I have a question about that and that particular thing.
Can we come back to it after I finish?
Yeah, okay.
Since we are running out of time. Okay, so I don't want to rush this topic, but so the next step are a set of trivial manipulations. It's trivial, but several steps of trivial manipulations in order to bring this into a form that you recognize. Okay? So what I'm going to do, first of all, I'm going to write this for the renormalized field. We got rid of this term. We set that equals to 1 for the renormalized field. Therefore, the first term will be d3k 2 pi cubed 1 over 2 omega exponential of minus I x1 minus x2 times k. Right, so minus I k times x1 minus x2 plus the rest. The question is what we are going to do the rest. The rest we are going to write, so plus the dot dot terms. To write the dot dot terms, introduce a function, we are just defining it. Sigma of q squared by the following relation. So first of all, we will demand that since we said that we are considering only the states with positive energies, we want to make this explicit. And amazingly, this power here is 3 instead of 4. Here, if I am writing everything in terms of renormalized field, I can write in terms of renormalized field and multiply by z. But I do not want to, I'm just leaving it as this. It should be clear from the context. We will not need the explicit form of this term for time being. What I'm saying that if you take the expression before, now we have separated one particle states and we have separated the ground states. Therefore, here this Pn should start from the, if there are bond states, it should start from the bond states. If there are no bond states, it should start from 4m squared. Okay? Therefore, this function will be 0. So sigma of q squared will be 0 if q squared is less than 4m squared. Because if it's less than 4m squared, the contribution from this sum has already been taken care of. Let's assume that there are no bound states. And the next thing is that that this expression, I'm going to write this and stop, because otherwise I have to go very fast and I don't want to do this. So I'm going to write this whole thing as delta plus x1 minus x2 times x1 minus x2 m squared. The mass which enters there is the physical single particle mass plus d4q divided by 2 pi cubed times sigma of q squared times theta of q0 times exponential minus iq times x1 minus x2. You see that if you substitute for sigma times theta from there, this expression, integrate over q, because of delta function, you will recover the sum. So we have just rewritten the sum. We haven't done anything more than that. Using the delta function, we have rewritten the sum. In doing this, we have also made sure that only the positive energy states contribute by putting this theta there. Okay? And sigma being 0 for q squared equals to 4m squared, we are also making sure that in this sum, only the prime sum contributes. That means ground state and single particle states will not contribute. It's clear? Actually, I'm almost there. No, let me stop. Otherwise.